Success is not what you dream, but the reality in which you live. Beginning of Amity University, Madhya Pradesh has been very subtle and calm, but filled with excitement and positive attitude.
A very warm and pleasant morning, ladies and gentlemen. I, Dr. Ritu Kumari of MIT University, Madhya Pradesh, Gwalior, take a great pride in welcoming you all to inaugural session of International Workshop on Recent Trend in Applied Mathematics for Engineering and Technology. The main objective of the workshop is to bring together leading academic researchers, research scholars to share their knowledge in different fields of mathematics and interdisciplinary areas. Participants can gain insights into the latest developments and application of mathematics in engineering and technology. The workshop can help attendees develop new mathematical and analytical skills applicable to their fields and get exposure to advanced problem-solving techniques and methodologies used in contemporary research and industry applications. We have experts from leading research institutes and universities around the globe here to deliver talk. To begin with, let us fold our hands together for Swasti Vanna in virtual mode to mark the inauguration of the workshop.
निःशेषजाड्या वरदां शारदा।
Thank you, Rajat sir. Now it's our proud privilege and honor to introduce Lieutenant General V.K. Sharma sir, Ati Vishesh Seva Medal, the Honorable Pro Chancellor, MIT University, Madhya Pradesh, Gwalior. Lieutenant General V.K. Sharma sir joined the renowned National Defence Academy and passed out a permanent commissioned army officer from the Indian Military Academy on 31 March 1972. He was granted the President Commission in the Corps of Signals of Indian Army and served the Indian Army for almost 40 years and retired from the second highest rank of Lieutenant General, which is a 3-star and a flag rank of the Army. Lieutenant General Sharma sir has also been an excellent academician, an extraordinary administrator, and a leader par excellence. Lieutenant General V.K. Sharma sir was the founder, Vice Chancellor of MIT University, Madhya Pradesh, Gwalior. Under his leadership, MIT University, Madhya Pradesh has grown by leaps and bounds and has been adjudged the best private university in Madhya Pradesh. He has also been instrumental in introducing a host of best practices to foster academic excellence in the university. Now I would like to invite the Honorable Pro Chancellor, sir, for his opening remarks. Please, sir.
Very good morning. Thank you very much, Dr. Ritu Kumari. Professor Dr. Santosh Sharma, the convener of this workshop today, Dr. Rajat Vaish, Dr. Ritu Kumari, Dr. Amnish Vaishwar, Dr. Ramkumar, all faculty members of MIT University, Madhya Pradesh, who have joined us online to attend this workshop. Dr. Anand Pratap Singh from IIIT Surat, India, who will be giving a talk on theory of fuzzy transforms and its applications after I finish my opening remarks. All the faculty members, staff members, and my dear students and participants who have participated in this workshop on recent trends in applied mathematics for engineering and technology. A very good morning to you all and a hearty welcome to everyone who is present online. Mathematics per se, people find it boring in today's world. Pure mathematics is not being opted for by very many individuals today. But we must not forget that human beings' life and intelligence is almost impossible without mathematics. We start counting the day a person is born, number of days spent, number of years spent, number of birthdays that is over, amount of property one has, the money one has, how much one has to pay the money, how much one has to earn the money, how much money is to be paid for various services. So counting and mathematics is there everywhere. To say that somebody can wish away from mathematics is impossible in a person's life. The mathematics introduced some very important concepts like infinity and zero, prime numbers, and much more. But today we are here to discuss about applied mathematics. In engineering particularly, and today any student who's done his 10 plus 12 with science, physics, chemistry, mathematics, you ask him or her, what would you like to pursue? 85% of the cases, they will say we would like to pursue computer sciences, CSE. Because today, the internet is on the go. The number of net users are rising every day. The number of mobile applications are increasing day by day. The number of fraud cases which are happening online are increasing day by day. and the number of research papers which are being written, the number of publications and inventions in science and technology are also increasing day by day. Now, in all these, the presence of mathematics is inevitable. When it comes to cloud computing, wherever the word computing comes, applied mathematics comes in. In communications, particularly mobile communications, satellite communications, fuzzy logic, robotics, mechanical electronics, what we call as mechatronics, even in biotechnology, biochemistry, biosciences, applied sciences, everywhere the presence of mathematics is there. Question is, pure mathematicians who are teaching to the students, they find it very difficult to separate applied mathematics from pure mathematics. And they sometimes tend to lay more emphasis on pure mathematics, which the students find it dull and boring to understand and rather tough. Pure mathematics, even applied mathematics, requires certain amount of concentration, certain amount of learning, and certain amount of rote learning also. One of the seminars, I remember I was talking to the students, and one student got up and asked me, "Sir, why should we remember some of the formula in mathematics? They are all there on the web. They are all there on the Google. Why must I be forced to remember those formulae? Why I must remember some of the equations and some of the notations and some of the constants, their values? Why should I remember once they are there?" So my answer to him was, you buy 11 or 12 books, each book costing 12 rupees each. Will you take out your calculator at that time and start finding out what is 12 by 12? He said, "No, sir." I said, "Then you will remember 12 by 12 is 144. You will remember that, right? Tables you will remember, you have remembered. The sequence of the days from Sunday to Monday you have remembered. The sequence of the months you have remembered. So similarly, there are certain things which must be remembered by mind. They must be remembered by heart. So therefore, you cannot afford to forget them. Otherwise, you will be so much dependent on your mobiles or on your computers or on your applications that your own brain will stop functioning. Today, unfortunately, we have become so dependent on Google, so dependent on online answers, that every small thing we look for an answer from the Google. So therefore, our minds are not open to new learning. And if your mind are not open to new learning, then creation of new knowledge, which is there every university's job, remains unfulfilled. The quantum physics or quantum mechanics is something very important. And some of the formulas that we see, like Laplace transforms, Fourier transforms, and some of the other equations which are there, those find direct applications. Even Maxwell's equations find direct application in various aspects of engineering, the way that things happen practically. So the mathematics has got two roles. One is a real word which is there. From there you can derive it, give it a mathematical equation. Anything which is happening can be given a mathematical series or a mathematical equation. Simple harmonic motion, for example, even sine wave propagation. So all these can be mathematically defined. Also, some things are mathematically defined and later on found that something that had been defined earlier, it has been found to be true, which is very rare. One of the cases is Maxwell's equations. Maxwell had discovered the propagation of electromagnetic waves through the Maxwell equations, but later on, when the electromagnetic waves were actually discovered, and it was found that they actually follow the Maxwell's equation for their propagation. Similarly, E is equal to mc square, which was discovered by Einstein, was a formula which was discovered. Later on, it was found that it is true that entire mass and energy are interconvertible with the equation E is equal to mc square. So with all these things, the applied mathematics finds much more importance in engineering, science, biotechnology, physics, in all fields of science or technology that we can think about. Fuzzy logic, optimization, conversion of real world, linking it to mathematics is something which is very important. And there we can find innovation, and we can also find ways and means to connect and to take the mathematics forward. The recent trends in applied mathematics for engineering and technology is a topic which is apt, which is very relevant in today's age, especially when the internet is on the increase, when the innovations are on the increase, when the number of publications are the increase and number of patents being filed are on the increase. India as such is trying to make a place for itself in its economy, economic growth, also scientific and technological growth. Economic growth and educational growth cannot take place unless there is growth in the mathematical field also. So with this, I congratulate, first of all, Dr. Santosh Sharma and his team who have joined together to organize this workshop on 3 days, and which will contain technical sessions from the experts on various subjects. And I wish this workshop a great success. So thank you very much, and Jai Hind.
Thank you so much, sir, for enlightening us with your inspiring and motivational message. With due permission, I would like to start the event, sir.
Please go ahead.
Thank you once again, sir. Now we move toward the plenary talk sessions. Today, we have with us first speaker, Dr. Anand Pratap Singh. Before his address, it's my pleasure to introduce him. Dr. Anand Pratap Singh is working as an assistant professor in the Department of Applied Mathematics and Humanities at the Indian Institute of Information Technology, Surat. Dr. Singh obtained his PhD in Applied Mathematics from the Indian Institute of Technology, Dhanbad. After completing his PhD, he worked with the Institute of Research and Applications of Fuzzy Modeling, University of Ostrava, Czech Republic as postdoctoral researcher. He is a member of International Rough Set Society, the Society of Applied Mathematics at ISM Dhanbad, and Calcutta Logical Circle. He served as a president of Siam USA student chapter of IIT ISM Dhanbad from 2015 to 2016. His research focuses on fuzzy sets and systems, category theory, fuzzy automata, and rough set. He has published several papers in national and international reputed journals. Now I request Dr. Singh to deliver his talk on the topic theory of fuzzy transforms and its application. Please, sir.
So thank you, ma'am, for your uh, brief introduction about me. And with this, I would like to start my talk. So let me share the. Is the slide visible?
Yes, sir, it's visible.
Okay, so good morning, all the participants who joined this workshop. And today I'm going to present a very nice theory that is called the theory of fuzzy transform. And basically, this theory is, let me say, in a more general sense, which deals with where we have the uncertainty in the classical transforms. So I hope you So starting from these are the outlines. I will start with the example of a classical transform, which is a Laplace transform. Then I will introduce how the theory of fuzzy transform works in a more general sense, and what is the uh, advantage of using fuzzy transform, and how this theory can be applicable to the various problems. So, so as you can see that I have taken an example of a classical transform. So there are various classical transform. Let me say Fourier transform, Laplace transform, Webley transform, uh, and the idea behind all these classical transform is based on transforming the problem from one domain to another domain. So if you say, for example, Laplace transform, so it transforms the problem from time domain to a frequency domain. And the reason why we do this, because there may be some problem which are complex in the original domain. So using the technique of transform, we can trans transform the problem from one domain to another domain where solution is simpler. And then we can solve the problem using the techniques from algebra and uh, linear equations. And for each direct version of transform, we have the inverse transform as well, right? So once we have a solution of the transform, then we can use the inverse Laplace transform or any inverse transform on the solution to return back to the original space, right? So this is the whole idea of any classical transform, that for any complex problem which are which are not directly solvable, or which may be solvable but the solution is quite complex, we can use the transform to convert the problem to a new domain where solution is simpler, and then we can apply the inverse transform to revert back to the original space, right? So the fuzzy transform, what I'm going to define, follows the same idea, but it has one more advantage, that here we can also introduce fuzziness or uncertainness we can consider, right? So the main idea of fuzzy transform is that it establishes a correspondence between a set of continuous functions on an interval as well as the set of n-dimensional real vectors, right? So it means we apply fuzzy transform to a function which is any continuous function, in fact, and it transforms the set of continuous functions to a set of n-dimensional real vector, right? So once we have n-dimensional real vector, then we can use the inverse transform and to use the technique of uh, from the uh, linear algebra to solve such problems, right? So this is the main idea of fuzzy transform. The advantage of F transform, as I said, for other classical transform is that it maps an object from its original domain into another domain, and manipulating the object in the target domain is much easier, right? So as in the case of example, what I mentioned in the very first slide, that dealing problem in original domain may be complex. So we can use the concept to transform from one domain to another domain, and then we can use the inverse version of the set transform to revert back to the original space, right? So the fuzzy transform follow the same idea, and the reason why we follow is that to reduce the complexity. So before moving forward, I will like to just give you an idea about what a fuzzy set is. So basically, a concept of fuzzy set is a let me say the more general version of the classical set, where we have only two uh, options, uh, whether an element belong to the set or not belong to the set, right? So that is the case of binary logic, where we have the values either 0 or 1. If something is happening, then we give the value 0. If something is not happening, or if it is not belonging, so we give it the value 1. But unlike the case of classical set, in fuzzy set, what we have advantage, that we can define a membership function which takes a values from any real number, and the output value is between close interval 0 and 1, right? So 0 means when we have something which doesn't belongs. 1 means when it fully belongs, and anything between 0 and 1 means when there is some partial belongingness, right? So we can give some a degree that up to what degree some element is or some element belongs to a particular set, or some object belongs to a particular universe, right? So if it is 0 and 1, so that is the case of classical set. But anything between 0 and 1, we will have some membership value. Okay. So the main tool in fuzzy transform is based on fuzzy partition. So it is defined, or it is basically a class of collection of the continuous membership functions, and which form of fuzzy partition. So fuzzy partition, if you have idea about the classical partition, that classical partition means we are given some data set and we partition the interval into different sub-intervals, right? So that is the case of classical partition. In fuzzy partition, we use the similar idea, but we give some degree of membership, some values for each partition. So there are some set of criteria which must be satisfied for any partition to be a fuzzy partition. So the first property is that is called the normality property, that for any partition AK at any dataset value xk, that must be equal to 1. And if the data x, or if the point doesn't belongs to this particular interval xk minus 1 to xk plus 1, so this membership value will be 0. The If you talk about a particular integral, particular interval xk minus 1 to xk, so the nature of fuzzy partition will be that it will be increasing, and in case of the interval xk to xk plus 1, the nature of fuzzy partition that it will be decreasing, right? And the last property is that if you take the sum of all these fuzzy partition element, let me say a1, a2, an, so that sum must be equal to 1, because basically it is a degree of belongingness in the closed interval 0, 1. So whatever a1, a2, different membership values will have, their sum must be equal to 1. So here you can see that we have a closed interval a to b, and there are sub intervals, let me say x1, x2, x3, and up to xn, right? And these are the different fuzzy partition a1, a2, ak, and an. So for each values of x1, we have some membership grade, which is between closed interval 0 to 1, right? For similarly, at the point x2, we have some values in this interval, closed interval 0 to 1. And you can see for each nodes, right here, x1, x2, x3, these are the node point. So at each node, the value of a1 is equal to 1. And between these nodes, we have some partial value. Let me say at this point, the value is something between 0 and 1. At this point, some value is between 0 and 1, right? So this is the case for uh, all other fuzzy partitions. Okay. So I have taken the few examples of various fuzzy partition with different membership functions. So the most common membership function we have is the triangular membership function, where we have the shape of uh, partition, which is triangle shape, right? You can see this. And the other membership function is sinusoidal membership function. And there may be possibility that membership function is both mixed version of sinusoidal and triangular membership function, right? This is the case of this diagram 3. And there are other different function, cosinusoidal membership function. So that is depend on what kind of membership function you define while using the or while taking the fuzzy partitions, right? So when we talk about any partition, so there is two possibility, either that partition will be uniform or it may not be uniform, right? So when it is uniform, so what does it mean? Uniform means the interval or the spacing must be have this equal width, right? That the difference between x2 and x1, difference between x3 and x2, what are the node points, that must be same. So we can say that h is nothing but b minus a by n minus 1, where b is the last node point, a is the first node point, and n minus 1 is the that can be calculated based on the total nodes point, right? So if the fuzzy partition is uniform, so it will satisfy these two criteria. That means the membership values will be uniformly distributed, and we can generate a fuzzy partition a1, a2, an uh, defining by this function. So this function produce basically a triangular shape membership functions, right? So here I have taken a fuzzy partition uh, to generate a triangular membership functions. So let me introduce the definition or the main version of fuzzy transform, that is in integral form. So there are two kinds of transform. One is based on integration, where the input is continuous function, and if the input is not continuous, so that is the case of discrete transform, right? So the first version of transform what uh, I'm going to discuss is the integral version of fuzzy transform. So as I mentioned, that for fuzzy transform, the input is set of continuous function from closed interval AB, right? So this CAB denotes the set of all continuous function f in the interval AB to some real number, right? And the other information what we require is the n fuzzy partition A1 to an of the interval AB. So these two things we require to define the fuzzy partition. So this two fuzzy transform. So fuzzy partition I have already defined in the previous slide, and f is any continuous function from the closed interval AB to some real number. So the direct version of fuzzy transform, which is in integral form, is nothing but these are some real number identified by f1, f2, and fn. And the formula or the expression to compute the fuzzy transform is that a integral a to b fx a k x dx. And in the denominator, we have a to b a k x dx, right? So if you look at this expression, so if you compare this expression of fuzzy transform with any classical transform, so this fx is nothing but a continuous function on which this f transform is being applied. And akx is playing a role of kernel, right? So if you have some idea about any transform, let me say Laplace transform or Wavelet transform or Fourier transform, so you must have learned or you must have heard about the kernel, right? Like in case of uh, Laplace transform, the kernel role is played by the exponential function. So here in case of fuzzy transform, the role of kernel is played by the fuzzy partition AKX, right? And if the partition is normalized, in that case, this uh, integral a to b AKX dx must be equal to 1, right? So in some sense, this definition of fuzzy transform is if you have idea about the weighted arithmetic mean, what it says, we have some functional value multiplied by the corresponding membership degree, right? Where A1x, A2x, and so on. So let us see how we can compute the direct uh, F transform for a given function. So to illustrate it, I have taken one continuous function, which is function x square in the interval, closed interval 0, 1. So just to illustrate, I have taken one closed interval and a continuous function x square, and the fuzzy partition of this continuous intervals are different fuzzy partition A1, A2 up to A5, right? So the first thing is to divide this continuous interval 0, 1 into 5 sub intervals. So you can say that the initial point is 0 and the final point is 1, and other intermediate points at 0 to x1, x1 to x2, x2 to x3, right? And since n, the number of sub interval you wanted is equal to 5, so we can find h equal to b minus a by n minus 1. So we can get the interval spacing. So let us see how we can compute it. So the first fuzzy transform can be computed by the computation of fuzzy partition. So A1x is 1 minus 4 times x, where x belongs to closed interval 0 to 0.25, right? Because the interval size is, the complete interval is 0 to 1. If you divide this interval into equal subintervals where n is equal to 5, so that will be the first interval will be 0 to 1 by 4, right? Which is equal to 0.25. And if you put this values a equal to 0 and b equal to 0.25 in the formula, what I showed here, to generate the triangle function, what we will get? We will get this value is equal to 1 minus 4x, right? So once we compute the interval, this fuzzy partition A1x, so now we are ready to apply this fuzzy partition in the formula of direct step transform. So what it says, that f1 is nothing but equal to a to b. Here a is equal to 0, b is equal to 0.25. The function value, what is the function value here? X square, and this is multiplied by the fuzzy partition. Yeah, if you recall this definition from here, a to b fx into akx dx, right? And we have assumed that this partition is normalized. What does it mean? This summation a to b, this integral must be equal to 1. So in denominator, we do not require anything. So let us see it, right? So if you integrate the first component of fuzzy transform, the value is equal to 0.01, and which I have denoted here by some blue dots on the graph. Similarly, we can compute some other fuzzy partition. So the second fuzzy partition is A2x, which is between 0 to 0.25. The function is increasing. That is the midpoint of this fuzzy partition. And from 0.25, which is in the center, to 0.5, right? You can see here, this is the 0.5. The function value is decreasing, right? The nature of partition value is decreasing. And this red color graph is for the parabolic function. So this membership function A2x is nothing but 4x. That is the equation of line joining this 2 point. Here coordinate is 0, 0. Here coordinate is 0, 1 by 4. And if you use the concept of equation of line joining these 2 points, which can be computed as y minus y1 equal to tangent times x minus x1, you will be able to compute that value is equal to 4x when the data x belongs to this interval 0 to 1 by 4. And whenever the function is decreasing, that is the nature of partition is decreasing from top to bottom here between 0.25 to 0.5, the value will be 2 minus 4x. And that can be also computed using the equation of lining joining these 2 points. The coordinate of this point is 0, 1 by 4, and the coordinate of this point is 0, 0.5, right? So you already have information about x1, y1, x2, y2, then you can be able to find the equation of this line. So once we have this component of fuzzy partition A to X, then we can calculate the fuzzy transform with respect to the formula we have introduced, right? So which is given by the function value multiplied by the fuzzy partitions. If you put this in the formula, so we will have, there are two subinterval. So in first subinterval, the nature of function is increasing from 0 to 0.25. So this will be calculated using this. And then in the second subinterval, the nature of function is decreasing. So we have 0.25 to 0.5, the second partition value, which is multiplied by the continuous function. And if you evaluate this integral, so that will be automatically equal to approximated by 0.0508, and I have denoted 0.08 some over here on the parabola, right? So this is another fuzzy transform component. And similarly, if you go forward, so we can compute again the third membership function A3x using the technique what I mentioned, and the third component is 0.26. The fourth component can be computed using the same idea, and it is equal to 0.58, right? And the last component is can be computed, which is nothing but equal to 0.85. So basically, what we are doing with this fuzzy transform, that we are approximating this function f by this different component of fuzzy transform. So you can see that the actual function f, which is a parabola x square is in red color, is now converted to a real number f1, f2, f3, f4, f5. So what I mentioned in the beginning of the fuzzy transform, that it establishes a correspondence between set a continuous function to a to a any vector in to a real vector in Rn, right? So we started with a function which was continuous, and after applying this different F transform component, you can see that this F1, F2, F3, F4, F5, these are nothing but some real number in the closed interval 0, 1, right? So these are called the different component of F transform with respect to this fuzzy partition, right? So I believe you must be able to at least understand that the role of fuzzy transform and the role of fuzzy partition in calculating this different component, right? Because the formula require the A1, A2, A3, A4, A5 for the computation. So to moving forward, the main property of this transform is that which is called the minimization criteria. It is something similar to the least square criteria, that it minimizes the function with respect to this property, right? And similar to the other concept of transform, that if you apply any transform to the set of continuous to some constant value, it produces the constant value, right? For example, if you calculate the Laplace transform of some constant c, it will produce the value c, right? So the F transform also plays a similar role. And if you compute the F transform of some constant function or constant value, it will produce the different constant. So the another property which most of the transform have, that is called the linearity property, right? So if there are some two functions f and g, and then the direct version of f transform can be applied on the linear combination of the function f and g, where alpha, beta belong to some real number. So for any real alpha and beta, the linear combination of this function f and h can be written in the form alpha times f plus beta times h. And if you apply the f transform on this linear function, it will be distributed, that is the constant times the functional value of function f, and the another constant time the transformed value of function H. So such property is called the linearity property. Now comes to the another version of fuzzy transform. So as I mentioned, when the data set or when the function is given which are continuous, so we use the integral version of fuzzy transform or integral version of any classical transform. But if you want to apply some technique in the real life problem, what we require in general, the most of the real life problem is based on some data. So for data to be applicable in any tool or any method, we require the discrete version of fuzzy transform. Okay. So here we have what we have considered. There are some interval a, b, and some node points x1, x2, xl, and then corresponding a1, a2, an are the fuzzy transform. The fuzzy partitions, and these are different nodes. So in that case, the another property or another criteria that the sum of this partition value must be positive, right? Only then this definition will make sense. So we have some fuzzy partitions a1, a2, ak. So the discrete version of fuzzy transform is defined as given by this formula, right? So if you look here, I have replaced the integral sign by this summation, and that is the case of discrete transform. And the function value at this different data points and their corresponding fuzzy partitions value, right? So we can use this discrete version of fuzzy transform to solve problems where we have some given data set and we want to apply the concept of fuzzy transform to solve the problem. It may be the problem of differential equation, it may be problem of partial differential equation. So as I said, the fuzzy transform plays a similar role as the other classical transform. So, and for each transform, we have the inverse version of fuzzy transform, right? So the rule of inverse version is that we have a problem in original space, and then we use the transform to take the problem from one domain to another domain to solve the problem in new domain, and then we require the inversion of transform to revert back to the original space, right? So similarly, for fuzzy transform, we have the inverse fuzzy transform, and which is defined as f cap, and which is nothing but the summation of the f transform component multiplied by the corresponding partition, right? So if you remember, while I define the direct version of transform, this role of fk was here, and the function for which we were calculating f transform was here, right? So once we define the inversion, the role of this the component of f transform and the functional value will be switched. And if it is non-Roots-Spinny means when this summation is not equal to 1. When the denominator sum is equal to 1, the inversion will be like this. But if it is not equal to 1, our expression will be given by this. So till now, what I discussed, that we have a direct transform, we can apply the direct transform, whether it is integral or whether it is continuous, to some data to calculate different component of a fuzzy transform. So the best property of this inverse fuzzy transform is that the uniform convergence property, right? So if you have some sequence of fuzzy partitions, and then the sequence of inverse fuzzy transform will be uniformly converges to the function f. So here the function f is the same function for which we calculated the direct f transform. So what does it mean? We have a correspondence between the inverse f transform and the corresponding function f. So uniform convergence means the nature of this convergence will be depend on the choice of this data set X as well as the choice of the epsilon, what we will choose for this uniform convergence criteria, right? So basically what I am saying that this inversion of F transform, what we will get are inversion of any function which can be approximated by the function F. So the transform what I am discussing is like it produce a approximation to a function F on which this transformation is applied. So now I'm switching to another new version of F transform or fuzzy transform, which is based on some lattice theoretic operations. So uh, lattice theory is based on discrete mathematics, and it requires some idea about some information about the partial ordered set in which we have suprema and maxima, suprema and infima of every pair exists, right? So now rather than taking the closed interval 0, 1, what we were using while defining the fuzzy transform, that its codomain or its range will be closed interval 0, 1. Here we will use the concept of lattice valued fuzzy transform. So basically, it is a new approximation models which are formally represented using weaker operation than the arithmetic one. So that is one of the beauty of this lattice valued is that rather than using this operation of uh, multiplication, here we will use the operation from the lattice which uh, considered to be weaker operations than the arithmetic operation. The another importance of using the lattice theoretic, defining the lattice theoretic transform is that it is based on fuzzy if then rules, right? So if you look at the most of the problems uh, in uh, in uh, in electrical engineering are this uh, where we deal with the fuzzy modeling concept, which is based on this if and then rules, where we have some set of antecedent and some set of consequence, right? So you can use this theory of if then rules to model the continuous function, and this theory is also or the lattice value F transform is also prepare the base for the theoretical development of fuzzy transform. So let us see how we can define the lattice version of this. So before moving to the lattice version F transform, we require some information about the lattice structures. So the basic structure of lattice, which will play a role of values or role where the functional value will be coming, is complete residuated lattice. So it is an algebra given by uh, a lattice L with the operation of meet and join with some binary operation and implication, and this is the top bottom element and the top element, right? So the first property is that this expression must form a complete lattice, right? That is L with infimum, supremum, the top element and the bottom element must be a complete lattice. The second property is that it must form a commutative monad. So monad means a semi-group with identity. And the third operation, which is called the implication operation, and we also call it the residuation operation, that must also be satisfied. So this residuation in the sense that if you have two elements from the lattice A and B, which are less than C, so this property holds if and only if the first element is less than equal to B implies C. And this property is called the residuation property. So we will take complete residuated lattice as a value set for defining the lattice valued F transform. So let us see. Right. So there are some terminologies and notation what I will carry forward, that L will be denoting the complete residuated lattice. the fuzzy set considered here take the membership values in L. So as I said, like the general case where fuzzy set take the values from closed interval 0, 1, here we have a more general structure than the closed interval 0, 1, right? Because in closed interval 0, 1, we have the just uh, the operation from the arithmetic one, but once we will extend this structure to the residuated lattice structure, we will have more options of operations from the lattice theory. Okay, and core of a set is defined as where the membership value is equal to 1, and any fuzzy set is called the normal if it has a non-empty core, right? So normal fuzzy set means here its membership, it must be, its core must be some non-empty set. So these are some terminologies which I will use. There are some basic relations and operations based on the fuzzy sets. If there are two fuzzy sets from the lambda mu belongs to Lx, so Lx basically denotes any mapping from set X to real number to a lattice L, right? That is, lambda is a map from set X to L, mu is a map from set X to L, and we denote it by Lx. So if two set lambda and mu are equal, so their membership value will also be equal. Similarly, the other operations are of inequality, union, intersection, multiplication, and implication. And a fuzzy relation, which is a more general of or more general version of classical relation, where we do not consider the case of uncertainty, that up to what degree something or some element is belonging to another element, right? So here the relation it's called fuzzy relation if it is a fuzzy subset of x cross x. That means if x is belonging to x, so what is the degree of this belongingness, right? If I say it is belonging to 0.5, 0.6, so that is the situation of fuzzy relation. And it is reflexive if Rx x is 1, and it is transitive relation if this condition is satisfied. So like the case of classical where we have x related to y and y related to z, that must implies x related to z. What we have here, if x is related to y with some degree, y is related to z with some degree, so x must be related to z with some degree, and this product of this degree must be less than the product of or the belongingness of x to the z with some degree of membership function, right? And it is called the fuzzy preorder if the relation is both reflexive and transitive. So any reflexive and transitive fuzzy relation is called the fuzzy preorder relation. So next we have the another theory that is useful to deal the uncertainty. For example, the fuzzy set use the concept of membership function to deal the uncertainty, and rough set is also applicable to deal, it is also useful to deal with the problem with uncertainty, but the idea of rough set is different. Here we use the concept of relation, concept of equivalence classes, concept of equivalence relation to deal the uncertainty, right? So this theory of rough set was first developed in 1980s by a Polish computer scientist Pawlak, and the rough set used the concept of approximation of a function, right? And it has a various application in feature selection, feature extraction, data reduction, pattern extraction, pattern matching, right? Because if you go behind the theories of this feature selection, feature extraction, and data reduction, which is based on some kind of relation, some kind of equivalence relation, right? So since rough set theory is based on equivalence relation and equivalence classes, so we can apply the rough set theory for such problem of feature selection and feature extraction from a given data. So let us see what rough set is. So the basic concept in rough set is based on some uh, approximation space. So we have some universe U, which is a set, and R is a relation on U. So basically, R is a subset of U cross U. And now we are defining the lower and upper approximation of set X, which is a subset of U. So when I say lower and upper approximation, so I mean if some set is not crisp, crisp means the classical set. So we can approximate that set either from upper, either from lower, right? So this lower and upper approximation huge, or we can use the lower end approximation to approximate a set from upper and from lower, or you can say from globally and locally, right? So we have some set X, which is a subset of universe U, and this pair U and R is called the approximation space. So the lower approximation of set X is defined by this, and it is nothing but the union of all element X for which the equivalence relation or the Rx is certainly contained in.
Sorry for the inconvenience, participants. Speaker will join shortly. Kindly wait. Kindly be with us.
Okay, I'm sorry for any inconvenience due to some internet connectivity. I was disconnected. So now, am I audible?
Yes, you are audible.
Yeah, okay, all right. So I was talking about the lower and upper approximation, and which we also call it the approximation from locally, or approximation from above, and approximation from below. So the upper approximation of any function, which is defined as if you take the equivalence classes and its intersection with the set X, that must be equal to non-empty, right? And once we define lower and upper approximation of a set X, we define the boundary region that is nothing but the difference of upper and lower approximation. Right? So if this boundary region is non-empty, in that case, we call the set is rough, and the case when this upper approximation and lower approximation difference is equal to phi is equal to 0 if there is no difference. So in that case, the set for which we are defining or which we are introducing, that will be classical or crisp set, right? So there is always a possibility that when we use the concept of approximation, that this difference, that is the boundary region, may not be empty. So here you can see the diagram where we have the set of object, which is the bigger circle, which is defined as capital U, and I have taken capital X, which is in red color, in a red circle, which is a subset of capital U, right? The set of object means the universe, as you define in set theory, and the capital X is subset of U, and now we want to uh, approximate this capital set X from both locally and globally, right? So when I say approximating the set X globally, what does it mean? That is stated by yellow color. That is basically the upper approximation of the set X. And when I say that we are approximating the set locally, what does it mean? We are talking about the lower approximation, that is in the blue color, right? So you can see that the upper approximation, this red color circle is the actual set, that is the boundary of the set. So when we are approximating something from upper, we are getting some values which are also covered outside of this red color circle. And when we talk about the lower approximation, which is entirely covered inside the circular area or inside the set, right? So basically, we are approximating this circle or this set both from above and below. So as I mentioned, it is called a rough set if its boundary region is non-empty, otherwise the set is crisp, right? So boundary region is non-empty, means the difference between upper and lower approximation is called the boundary region. Okay, so this is the whole idea about the rough set. When we have some uncertainty in the data, we can use the concept of rough set to talk about the set of objects and then classifying the object based on how they are related, right? For example, we are given some set with some corresponding property. So a set X with corresponding property, Y with another property, Z with another property, then we can create a relational tables, and based on the relational tables, we can identify the equivalence classes. And here I have defined the use of fuzziness in the concept of rough set, what I mentioned here, that is using the uh, fuzziness in approximation space. So rather than considering uh, R here as just a classical relation, we generalize this R to a fuzzy relation. So this pair XR is called the fuzzy approximation space. And now we are uh, combining the theory of fuzzy set with rough set to produce a space. Here it was based on just classical set X. Here the set X was classical set, but now we are taking this set X to be a fuzzy set, right? So which is given by a operator from set of all fuzzy set from X to L to another set of fuzzy set to the set of all fuzzy set from X to L. So now our definition of upper and lower approximation is based on the operation from the lattice theory, right? So as I mentioned, when we talk about the classical definition, where we have the operation of union, intersection, multiplication, and division, subtraction, when we switch our terminology to the set of lattice operations, so this operation of union will be replaced by supremum, the operation of infimum will be replaced by uh, sorry, the intersection will be replaced by infimum. The intersection here between Rx and Ax is replaced by the minimum operation, and this subsethood property or inclusion property is replaced by the implication, right? So this is the expression for the lower and upper fuzzy approximation operator, right? So once we define this fuzzy approximation operator, then we can connect the theory of fuzzy transform with fuzzy approximation operators. So let us move forward. So if you look or if you observe this, so we found that an equivalence relation induces a partition of the universe. That is the case of fuzzy transform, because it is based on the concept of fuzzy uh, equivalence relation or fuzzy relation. And the theory of fuzzy rough set is also based on concept of some fuzzy relation or equivalence relation, right? Because the theory of rough set, we require approximation space where X is a set, R is a some fuzzy relation on it. That means we can connect these two theory of fuzzy approximation space and rough set to produce some uh, stronger applications, right? So these are some basic properties which the theory of fuzzy rough set satisfied. That is the properties of that we can apply this theory if two sets are A is contained into B or A less than equal to B, then their upper and lower approximation will also follow the same. We can apply the upper and lower approximation on the collection of union of this fuzzy partitions or union of this sets. And then this is the similar like the shift property, the fourth property, the property of constantness. And if the relation is reflexive, then we say that R, uh, the upper approximation will be contained into A, and the the lower approximation will be contained into A, and which will imply that the set A will be contained into upper approximation, right? So these are some properties based on this approximation operator, right? So we have the another space. So till now we discussed the space of fuzzy partition, space of approximation, and the another space is called the space with fuzzy topology. So write the classical topology here. The all the open sets are fuzzy subsets, and this collection X with this fuzzy subset tau X is called the fuzzy topological space, right? So it is basically a collection of open sets which are fuzzy and which satisfies the properties of uh, arbitrary suprema and finite infima, and contains all the constant fuzzy set. So this is called the fuzzy topology. So if you define the fuzzy topology, so we have concept of closure and interior operator. So the closure operator is defined as it satisfies all these four properties, where the C satisfies for any constant fuzzy set, it will produce the constant fuzzy set. For any set A will be contained into the closure of A. This is the preservance of union, and the fourth is the idempotent property. Similarly, we can uh, add some more property where this closure operator is applied over the arbitrary union of set A1, A2, and AJ, right? And the fifth property, when we have some constant fuzzy set A multiplied by some set, then it will produce the constant times the closure operator A. And similarly, we can define the relation between fuzzy topology and this fuzzy closure operator. So we can connect this uh, by defining a relation between upper approximation and upper approximation of set A with the set A. So basically, when we write like upper approximation of A is equal to A, we are saying that it is a fixed point of A, right? So if you take an input where A is the fixed point of the upper approximation of R and A is fixed point of lower approximation of R, then we can generate two fuzzy topology, which is based on open set as well as closed set in TR, right? So we can say that the theory of fuzzy transform and the theory of rough set, we can produce the upper and lower approximations, right? So here we have some associated topology, which is upper and lower topology, and which is in general Alexander topology based on this fuzzy pre-order relation. And we have here we have defined the fuzzy partition with the membership values from the L, which is residuated lattice, and it is defined as the collection of all ordinary sets which has a non-empty core, right? Since core of the sets form a partitions, what does it mean? The core must be non-empty. So here we have generalized the concept of fuzzy partition to arbitrary case, right? Rather than using I equal to 1 to n, here we are generalizing this concept to some arbitrary xi so that we can connect this uh, transform with the concept of fuzzy topology. So basically, we are defining a relation between these three different kind of theories of theory of fuzzy transform, the theory of spaces with fuzzy topology, and the theory of fuzzy rough set, right? So that can be useful for the various applications. So we denote space with fuzzy partition like X and pi, and we can represent fuzzy partition by a fuzzy relation. Okay, so as you know, for any given partition, you can construct an equivalence relation. From an equivalence relation, you can construct a partition. So in the same way, for any fuzzy partition, you can construct some relation where relation is given by R pi xy, where pi is some partitions, and corresponding relation is A I pi y at x. So I wanted to use this relation and partition to connect the theory of fuzzy transform and rough set. So here you can see uh, this relation is a fuzzy pre-order relation. That means it is reflexive. When you take x and y both are same, it has the value 1. When x and y both are not same, it has a value a xi x. So we can easily found that this relation is equivalence relation. And the direct fuzzy transform and direct lower fuzzy transform is defined like this. The partition multiplied by the functional value, the partition implies the functional value, right? So here, rather than taking the operations from arithmetic one, we are taking this operation of multiplication in the sense of lattice, and this implication are arrow operation that is also from the lattice operation, right? So here we got some connection between fuzzy transforms and the approximation operator, that now we can say that the direct version of fuzzy transform is nothing but the upper approximation of fuzzy rough set, right? So since we have represented this relation A xi by a uh, corresponding fuzzy equivalence relation, which is R pi xy. So we can write this upper and lower approximation in the sense of fuzzy upper and lower transform. So once we have this connection with fuzzy upper and lower transform, then we can induce some properties similar to the upper and lower approximation of fuzzy rough set, right? And the last relation is that we can connect a fuzzy upper transform as a Kuratowski fuzzy closure operator, because the Kuratowski fuzzy closure operator is connected with fuzzy rough set, and we have defined a connection between fuzzy approximation operator as well as fuzzy app transform. So we can say that the direct version of fuzzy transform is nothing but the Kuratowski fuzzy closure operator. And there is a continuous map between upper fuzzy transform as well as the corresponding fuzzy topology, right? So basically what I discuss here, that if we are given some function, so there are the theory of fuzzy transform is there are two ways. Either we can go toward the theoretical development of fuzzy transform, where we can use the idea from the theoretical topics. Let me say the approximation concept, what we study in approximation theory or fixed point theory are in fuzzy topology are a related structure. And the another approach of fuzzy transform is where it is applicable for the problem based on uh, differential equation, image restoring, image enhancing, data manipulation, and so on, right? So the first part of this talk where I discuss that fuzzy transform for the continuous as well as the discrete version, where I have showed an example by computing the different F component transform. It's applicable for the problem which are based on differential equation, uh, based on image processing, because you can use some data and corresponding partition in the definition of fuzzy transform to produce the better approximation of the given image, or let me say in a more general sense that the image will be represented in form of some function, right? So basically we discussed this connection between these three theories, at the theory of fuzzy upset, fuzzy topologies, and fuzzy transforms, and how we can use the concept of this approximation operator as well as the relation between interior and closure operator. Yeah, because interior and closure operator is nothing but uh, also have application in imaging, where we want to approximate some function from either from below or from above. And the last result, our last output, what I have showed, that the theory of fuzzy transform, it produces a continuous map between the associated fuzzy topological space, right? So I can say that the theory of fuzzy transform has a two side. One is the application oriented, that is the first part of talk, and the another is based on the already existing theory and their development, which will in fixed point theory, in fuzzy topology, or in other related structure where lattice theory play a significant role. Yeah, so that's it. And thank you from my side. If you have any uh, questions or any suggestions, so I'm open for that.
Thank you, sir. Thank you, sir, for such a valuable and knowledgeable session on theory of fuzzy transforms and theory of fuzzy rough sets and its applications. I can believe we can benefit from the session for innovative research, sir. Now, thank you, audience, for your attention. If you have any query, please ask to the speaker.
Uh, Good morning, sir. Here I am
Good
Dr.
morning.
Sanjay Mishra. And
Yes, sir.
uh, can you tell me some literature that is related to the fuzzy topology and here the fuzzy transform? Actually, I am working in topology, so
Mm-hmm.
just I want to just see some literature if you have, or you can
Yeah, yeah.
suggest.
Yes, sure, sure. You can just look on Google. My Google Scholar, you will be able to find various literatures on fuzzy
Okay. So
topology
you
as well.
already done the such type of the studies where the
Yes,
fuzzy
some
topology
studies.
and
Yes, some studies I have done, and something is in progress. So there are still to make some study related to development based on topology and related structures.
okay.
Yeah.
Okay. Thank you. Thank you. I will
Thank you.
definitely see that paper.
Yes, sure. You can mail me in case if you are not able to get the hard copy. Hard copy, or let me say the PDF version.
Thank you. Thank you.
Thank you.
Any more queries from the participant side? Thank you, sir. I, on the behalf of MIT University Madhya Pradesh, would like to thank you for giving your time to share your profound knowledge with us. The next session will start at 2 p.m. Kindly join with the same link, participants. Thank you once again.
Yes, someone wrote in the chat, suggest some textbook. So, Mr. Keso, you can find a book, an insight into fuzzy modeling, right? Where you'll be able to see the various application of fuzzy transform for, let me say, image inpainting, image manipulation, image enhancement, image processing, as well as the theoretical version of fuzzy transform. Also, that book will also cover the different application of fuzzy transform for the solving Volterra integral equation, partial differential equation, as well as the problems based on uh, fluid mechanics and heat equations. Yeah. Thank you.
Thank you, Bafu. Thank you so much.
Thank you.